provocations. I would actually maybe call this talk a provocation adjacent. It's an extension of the original one I gave. I'm trying to kind of embed it in a maybe more broad critique of what goes on in practice and point to some work I've done subsequently to try and address what I feel is a gap. So hopefully that works. So I'm going to talk about just designing systems and evaluations. I'm going to start pretty high level and then kind of narrow down into how I think things could be evaluated quite better. And so just at a high level, a lot of what we design is shaped by the information we work with, myriad information we can work with, but we tend to go towards a subset and the concepts we have, which have this embedded meaning. And then furthermore, these things actually, the way we design then shapes what information gets seen, what's visible, and what concepts are recognized, used, and discussed. So there is this kind of nice feedback loop. Sometimes people call it performativity. And this idea of concepts really, meaning-making things that we embed into design is something I want to distill because a lot of those concepts go into how we evaluate systems. So systems in particular are valued using claims about safety and relevant knowledge. And then we kind of codify these we construct measurable concepts. And these measurable constructs are meant to be inferences about the concepts we care about, that we make claims about. So this is perhaps not new to this crowd, this formalization. But I guess at a high level, the claim I'm making is that evaluation scores are statistical claims about value and should be treated as such. And that brings some uncertainty that a lot of people from various disciplines often contend with. First is this idea of value uncertainty. So what counts as good, for whom, with what trade-offs, and then also just uncertainty about what is the context in which that is relevant for our evaluations or for our understanding of the claims we make. And so evaluations draw conclusions from this information under assumptions about both. We tend to make assumptions without stating them. And so some examples. We have many kind of metrics or evaluations even we have to make claims. We take things like GDP, stock market, all these things, and we make claims about how good the economy is. Or we take your biometric data, BMIs, and make claims about how healthy you are, so on and so forth. We do this across a variety of settings. These things are everywhere. And you'll notice for the first three, there are several of these metrics that have been called into question as of late, perhaps GDP as a reflection of the economy, or BMI as a reflection of your health, SAT score as a reflection of someone's capacity. But I think we should critically analyze this often at the time of production, and do so also for predictions. So things like accuracy, AUC capability, we should be kind of questioning which ones we make or which ones we select. In ML, we don't often treat these with the appropriate epistemic consideration, or so I claim. So there are a lot of, famous, popular critiques of evaluation that I want to kind of contextualize what I'm going to, what my critique is about. So first, Goodhart's law kind of is one of the most popular. A lot of people here know about it, cite it. And that's just simply that once you put pressure on any kind of metric, post-deployment, via optimization or what have you, it ceases to be good or there are problems that can arise. So there are many instantiations of this claim. Also just that we have aggregate values, collapsing it all into one kind of hides our heterogeneity. Why are you using accuracy when you can use many things? And I think these are really important. They mostly happen on what occurs after something is adopted or optimized. And I'm going to refer to hacking value as something that happens kind of as we are thinking about design already. So that is, we delegate value to an artifact often without justification. I say we. This crowd is particularly conscientious. Maybe it's not you. Maybe it's others. But often when I read papers, people are not justifying why they're using the evaluations they are adopting. And so I have this little definition here that it's just working definition. But hacking value occurs when an evaluation is treated as if it's a direct measure of value, even though the value theory and the inferential assumptions required to justify this have not been stated or defended. And my argument is that if we actually make this estimate explicit, I would say at the time of design, as we're writing our papers or arguing with hospital administrators that you should deploy my solution, this would enable much more legitimate design, interpretation, and deployment. So by hacking, I kind of have this caricature idea in my head about what hacking is. It's kind of emerged as a way to build systems under uncertainty. We just iterate through observed variation, rather than having this ex ante justification of our objectives. And in particular, evaluation is kind of used in the hacking community as a stopping rule. So early evaluations were just use-based. Did people use what I designed? And something was good if just people used it. And of course, people adopted this, culture permeated without much thought. And then we deployed it in much, much higher stakes contexts without it being justified. And it took a while for people to criticize this. Canonical example is engagement maximization in Facebook. But that's kind of the analogy I wanted to have you guys hold in your mind as to what kind of codifies this. And of course, there are a couple of related insights I want to kind of call out. A lot of people have talked about this in one way or another. One notable kind of paper highlights that predictive optimization risks illegitimacy if decisions are not normatively justified. I really like this paper, fact paper by Angelina, in which they kind of construct 7 kind of common flaws, like a rubric, and say that these kind of proxy estimates are uncontroversial measurements of value or a valid input into a decision without modeling uncertainty or the normative choices underlying the estimate. So this is kind of an instantiation of what I'm talking about. There are other works that have also kind of tried to draw out this point, that oftentimes we have normative outcomes that we fundamentally care about, diversity, or we care about merit. And instead, we end up doing things like measuring for error parity or feature independence. But if we just kind of explicitly designed our systems to advance the outcomes we purportedly care about, as in diversity, then we end up with much better policies and evaluations. So I think this paper is kind of doing a lot of work to show that this is the case. And then I wouldn't be remiss for the shout out to power that often comes out, like who has the power to instantiate or codify value? And this is often tasked or credited with a source of illegitimacy. I think the last call out I'll make, or contextualization, is this idea of technocratic closure, which my other provocateur, Ben, pointed out the last time we were on stage together. My summary of his indictment about evaluation was that many real-world decisions cannot be necessarily reduced to uncertainty. They involve a litany of disagreements, judgments, and accountability. And technocratic systems tend to be designed to collapse all these conflicts into measurable constructs that can be then centrally optimized. And so you shift from judgment to optimization, displacing all these politics and disagreements with apparent objectivity. And technocracy is not necessarily about better decisions, but about decisions that can be administered. So it kind of narrows the decision landscape. So this is Ben's critique. I feel like I have to shout it out because I think it's somewhat related. It's not critiquing metrics. It's a critique of the way we settle value disputes without having to argue about them. On some level, it can be also kind of lumped into the power space. And hopefully I gave due diligence to his critique. OK, so what should be done? I'm just simply arguing that if we're going to use a score to compare, rank, make claims, then the value concept and inference assumptions should be stated and defended. And that ML evaluation sections, like in our papers, should start with the desired value and argue for why whatever their solution concept is and what their evaluation of it is a good proxy for inferring such value. These values are latent, varied, and contested, and deployment contexts are uncertain and stationary. Therefore, evaluation should be asking, there's a lag, so give me 2 seconds. It's like kind of jumping around. Okay, there we go. What does model behavior imply across plausible value realizations? Okay, so I'm gonna jump into like what I actually did after 15 minutes of setup. I just wanna take you through some work where I tried to think about how people are doing evaluation. This is kind of a combination of work that appeared in NeurIPS this year and one under review at AI Stats. Okay, so here are some examples that we started with. We partnered with a couple of my collaborators who are clinicians, and we were just trying to understand what are some examples of variability that we need to take into account. So one high-profile one is syphilis. If I'm a hospital administrator, I govern a region, I realize immediately that there's a lot of variability of syphilis rates across the US. So in fact, it could be like over 10 times the amount in some regions as compared to others, even in spaces that are somewhat close. So the familiar argument is that this test, whether we should deploy it, often depends on us knowing the base rate, but since they vary widely, how do we kind of capture this variability in terms of assessing what's going to work well across a wide region of the United States where I'm administering my policy. Another example would be prostate cancer. I don't know much about it, so I'm going to make some value claims about it. Some might claim that the value of surviving might be similar across patients. Now, of course, age might come into play. But the value of the counterfactual of potential incontinence, which could happen if you intervene just as a diagnostic measure by, for example, taking a biopsy, will vary widely among patients, and that patients might have different sensitivities towards how they feel about this side effect, potentially. So a doctor treating a patient might know that patient's value exactly, but the administrator who's doing the model selection for the healthcare system and has to be responsible for a wide variety of patients must choose a model that produces better outcomes. So how can we characterize this distribution of costs? Cost has also come up in several of the talks here. The last kind of two examples, these are all about health, but this comes up in the criminal legal system and a whole host of other settings, is about treatment of tamoxifen for breast cancer. There are various authorities that have kind of advocated different cutoff rates for when we should administer this kind of treatment. And we'd like to pick a model that allows us to make good decisions across this range, perhaps taking into account the entire kind of expertise. But one thing we can agree on is that maybe we'll rule out cutoffs that are well beyond 3%. And of course, there are many, many more examples that I could have highlighted. I just want to give a sense that whether it be costs or potential prevalences, the population is varied, and typically we have a range that we know of a priori that we want to encapsulate in our evaluations. All right, so down to what we did. So each evaluation metric corresponds to particular cost regimes and deployment populations. Choosing one metric silently chooses which deployment population is being assumed and whose cost matters. And in many domains, especially in clinical domains, costs and prevalences vary across people, and we want to formalize this. So we decided to use as our test bed classification, and in particular binary classification, where we map some inputs to binary decisions. We have a decision rule that's constructed by comparing a score perhaps to a threshold. This is typically what's done in at least healthcare medical settings. And we also have this notion of value that I'm going to introduce, and that's typically latently there, which assigns a value to each score given the true label and the classifier's decision. And so we might evaluate overall performance by this expected value over deployment distribution of this value. Hopefully everyone's following along. So a minimal model that we study in this paper encodes the concept of value for a decision A relative to the realizations we see using a table. So we have this kind of confusion matrix. This is very simple. It's kind of what we teach in Statistics 101. And so what we assume about this table for the deployment setting we're interested in is that a true negative at baseline is just 0, but that acting, treating or intervening, auditing, what have you, consumes some resources. And that happens no matter what the actual outcome is. And then also false negatives incur some downstream harm because you don't catch the disease. This is a popular value model advanced by Engstrom, who was a statistician in the 19th century, but it's used across a variety of settings. And the other kind of simplifying assumption is we normalize this matrix without loss of generality to take this harm to be 1. And that allows us to re-express this entire confusion matrix as just this ratio C over L, which captures how much we're willing to pay to avoid a miss. This is, of course, under some assumptions about the harms being much greater than the cost. Okay. So this cost model is nice because it allows us to express this trade-off in terms of like one variable, which is this ratio. Okay, so this allows us to express most things in this regret formalism. Okay, I think I have 10 minutes, so I'm doing all right. Okay. So regret measures the expected loss of a classifier relative to the ideal decision rule under this trade-off. So if we adopt our value matrix from the prior slide, then we can actually express this regret quite nicely in terms of like 3 terms that have nice coherency in terms of how we think about people's preferences. So the first is the class prevalence, pi. That's just a probability of the label being 1. The cost, as I said, C, which is just the relative cost of making mistakes, and then the CDF of the scores for positive and negative classes. So it's like really, really nice, in part because 2 of those entries were 0. It makes these things explicit and therefore highlights what fixed metrics abstract away often. So what can we do by characterizing things in terms of regret? So at this juncture, we kind of wanted to understand what people were using. And so we used an LLM. And what we found is that, this is for 2023, I believe, we found that most people were using accuracy. Our first takeaway was that for ICML, which is the popular machine learning conference, for those of you who don't know, accuracy was the most widely used, about 50%. The same was true of FACT, Fairness and Machine Learning Conference. CHIL, which is a machine learning healthcare conference, actually favored AUC ROC, which is what my provocation was about last year. So trying to attack that piece of the puzzle. And another takeaway is that other kinds of proper scoring rules, and I haven't really defined what a proper scoring rule is, but things I advocated for last year was like Breyer score and log loss, were very rarely, if never, used. Okay, so that's the baseline. The question is why? So what we tried to do is try to understand what accuracy and AUC assume about cost. And actually, these are based on somewhat well-known results in the statistical literature, but we just kind of wanted to start here to highlight it. So just to understand cost in particular, we'll do prevalence next. We assumed a fixed prevalence. And we assumed that the decision threshold was picked optimally. That way we're just looking at costs. And what we find is that if you can represent accuracy according to regret in this formulation, and what it tells you is that accuracy is somewhat optimal, it corresponds to this regret minimization when misclassification costs are equal. So if the cost of an error on one side is equal to the other. Now, this might make sense with certain like image classification tasks, but it doesn't really make sense for a lot of medical settings. AUC does something even kind of more interesting, which is that it averages the regret over a distribution of possible misclassification costs. So this is like a really weird thing that it's doing, but the distribution is over the model scores of data, and then it pretends that that's kind of representative of the distribution of costs. And so it corresponds to regret in this like setting, but it's almost like this domain mismatch. It doesn't quite make sense, but it gives rise to this intuition that AUC is taking into account a range of either costs or prevalences. Now let's turn to what I advocated for, which is the Breyer score. Yeah, I'm very close. The Breyer score is kind of nice because what it does is it averages over costs uniformly over 0 and 1. It's more flexible than AUC and our accuracy, but as I discussed at the outset, a lot of times our costs are in this bounded range. And so what we kind of did is figured out a way to map this onto a bounded threshold Breyer score where we can have the doctor or whomever state the range of costs they care about and actually evaluate their model based on that range of costs and then make comparisons. So it's trying to give more interpretability to based on information in the deployment context towards evaluations. Very similarly, we can do the same about prevalence. Accuracy is doing something weird when it comes to prevalence. It assumes that the evaluation data set matches the deployment prevalence, which is rarely the case in healthcare settings. Oftentimes there's this balancing of the labels or prevalences of instances of the disease and not, and it's way more balanced in production than it is in deployment. And AUC also does this weird averaging over the scores and pretends that's kind of close to the class label prevalence. And oftentimes it is, it's not completely unreasonable, but there's still this kind of weird mismatch. And so this was a little bit newer. So what we were trying to do is we proposed a simple formula to just simply average over some distribution of prevalences you know will take place. Here we did this with both the Breyer score and cross-entropy loss. So this hopefully gives you a way to evaluate things in terms of the domain knowledge you actually construct. So we actually have a tool, Breyer tools, to help support this valuation. If you know a cost range or relevant prevalence range relative to the real deployment that you will be deploying into. And I think what's nice about this is it encodes exactly the information that the practitioners routinely reason about and nothing more. So in particular, when uncertainty about costs or prevalences is neither a point mass nor spread uniformly over an interval, nor is it spread according to some score distribution, accuracy, AUC, Breyer, they impose these weighting assumptions that don't actually reflect a practitioner's actual uncertainty about the deployment scenario. And so what we want to do is take that uncertainty and subsume it into a coherent way to evaluate that takes these costs and prevalence uncertainties into account. So rather than ask practitioners to specify an entire distribution over these ratios of labeled distributions or of cost ratios, we argue that the most interpretable and decision-aligned thing to do is to represent some interval of uncertainty and then assume some sort of least informative prior, so uniform distribution over this interval. And so we found that this was kind of consistent with constraints. We have this nice tax table that taxonomizes which metrics actually make sense depending on the deployment context. If you have any kind of uncertainty, then these mixed threshold evaluations make most sense, but it makes sense depending on the decision type. The decision type being whether you can act independently, so each case stands alone, or whether it's more of this top case scarce resource ranking setting that actually sometimes you're in hospital context, but oftentimes you're not. And just as a summary, we did a bunch of stuff with Breyer tools. But the idea underpinning the whole thing is ideally so that people can avoid value hacking, state the reason why or what you think the deployment context is, and then evaluate according to it. That's kind of more or less what I was trying to motivate people to do. And I think developing more tools in that direction can have some nice, that are coherent and easy to use would be quite nice. So thank you for your attention. Hopefully I ended on time.
All right, let's have maybe one or two questions before we break for lunch. You want to start us off?
So I think it was 2 slides ago, you're running through why you wanted to go to the bounded threshold Breyer score.
Mm-hmm.
So if I keep following that through, I guess I would have thought like a maximum regret style thing across the set of thresholds between A and B rather than the uniform prior on top of that, because then you have this like guarantee that regardless of someone's.
Yeah, I think a next step that would be really nice, and it's not so easy to do this, is to instantiate any kind of distribution over some range that you know will occur. Maybe you don't want to treat everything the same. We started there and actually ended up being a little bit, we had to do this like kind of nice projected thing to make it all computationally feasible. And so there are other works, statistical works by Hand and others who have actually proposed like beta distributions over some region. But I think if you're a practitioner, it's hard to like choose beta priors that cohere well with what you know.
What do you mean?
I think it's just much easier to be like, okay, 2 experts told me this range is plausibly within this range. Let me just start there. I don't really know where it is. Maybe I do privilege one expert more than the other. Maybe a weighted thing would be nice as a next step. But giving kind of that nice way to adjudicate based on like how people think, that's more legible, I think, than these other things that do things implicitly, like AUC. It's weighting according to a score distribution you have no control of, and it makes it less coherent. So we have many reasons why. Also, prior scores are proper scoring rules. They have nice calibration kind of decompositions, and I didn't get into it, but I read the paper and hopefully use it.
All right, let's have one last question. Yeah.
Yeah.
Yeah, I'm wondering, I feel like there's some kind of tension between like having this kind of neutral, like I feel like hacking can go in both ways. Like you were kind of making the point that if you use one of these like neutral measures, like accuracy, that's clearly not satisfactory because you have like your particular problem domain where costs are different and so on. And people are like not justifying these metrics, right? But then you can go to the other extreme where like every person writing a new methods paper at all these conferences can come up with their own metric and they can make like a seemingly good argument for why this is not the right metric and they can defend it and make their algorithm seem really good according to that metric. And then it feels to me like you can have this extra layer of confusion for practitioners where like now they're like, oh, but this paper seems to make a pretty compelling argument and this other paper makes a compelling argument. And maybe they're all like kind of in the same problem.
I agree. I think there's like a middle ground. So what's nice about benchmarks is they do standardize things, but then I was trying to imply you get into this hacking territory where now everybody uses AUC without re-justifying it for its application area.Maybe like it'd be nice to have, okay, we're all designing machine learning algorithms for syphilis. We can agree on like this evaluation as like kind of a nice deployment scenario. Also, if you're a hospital administrator, you're not necessarily trying to like hack things. You're trying to deploy what's best given the context you know, and it would be nice if you had that like taxonomy. But I agree that if you shorten the interval just a little bit and it made your thing seem nicer than another person, that's a problem, and maybe people will get into this other hacking behavior.
So you think somehow, like, roughly speaking, like per problem domain,
Yes.
maybe we can agree
as a
on
community,
some metrics
exactly.
that are like a good summary.
Exactly.
And,
Exactly, and that would discourage the hacking, but also make it somewhat more domain specific rather than everybody adopting the same metric, regardless of if it's criminal, legal, or hospital settings or any other kind of setting. So I think it should be a little bit more fine-grained than it is now, but not too much. Little ground.
All right, so let's thank our speaker. And with that, I get to wrap up the morning. I am 3 minutes behind schedule, I'm sorry. We will see, hopefully, all of you back here at 2 o'clock. I'm looking at, Angela, is the poster session in the lobby right there?
Honestly, I don't know, but it'll be here.
Cool, it's gonna be here. It's somewhere here, probably right there. We'll make it work. But yeah, come back at 2 o'clock, and we'll see everyone this afternoon, and then again tomorrow morning. Thanks, everybody. All right, and I'm out.